The ocean does not keep secrets. It holds memories etched in the chemistry of its deepest trenches. It carries the history of continents in the slow drift of its currents. For eons, its voice was a language of cycles, a rhythmic pulse, the metronome of tides, the seasonal breath of ice at the poles, a planetary heartbeat so steady it was the very definition of constant. But something has changed in its timeless monologue. A new rhythm is emerging, a subtle but insistent acceleration. The vast blue heart of our world is beginning to race. The steady measure of the coastline, a line drawn by civilizations, is being quietly, inexorably redrawn. This is a story whispered in millimeters, a tale of planetary fever, and for the first time we have something that can listen, not with ears but with an unwavering gaze from the blackness of space. A sentinel whose only purpose is to watch the water. Humanity's relationship with the sea has always been one of duality. It has been a source of sustenance and a wellspring of myth, a highway for commerce and a graveyard for empires. We charted its surfaces, plumbed its shallows, but its essential character, its sheer volume, remained beyond our grasp. We measured its rise and fall against weathered posts in bustling harbours. Imagine a dockworker in 18th century Amsterdam or Liverpool. He stands beside a wooden staff driven into the harbour floor. Carved notches mark the water's height, a chronicle of the tides. This tide gauge, a simple yet revolutionary device, for its time was our first systematic attempt to quantify the ocean's behaviour. It was a local story, a narrative of one port, one piece of coast. For generations, these isolated stories were all we possessed. Thousands of such gauges scattered across the world's shorelines created a patchwork quilt of data, a fragmented understanding. Each measurement was subject to the whims of the land itself. The ground beneath the gauge might be sinking, a process called subsidence, or it could be rising, still rebounding from the crushing weight of ancient glaciers. The planet's crust breathes, and our yardsticks were breathing with it. We were trying to measure a shifting liquid with a shifting ruler. The dream, the desperate need, was for a single universal reference point. A fixed perch, utterly disconnected from the planet's geological size, from which we could observe the entire global ocean as a single unified entity. The aspiration was to see the whole truth of the water all at once. This fantasy, once the domain of poets and mad inventors, would require a vantage point that no human had ever occupied. It would demand a journey above the sky itself. To truly comprehend the monumental leap in perspective we have achieved, consider our world as an immense celestial bathtub. For millennia, we have lived inside this basin, watching the water level. We would stand at one edge, dipping in a stick, noting the mark. Then we would walk to the other side and do the same, unaware if the tub itself was tilting or if the floor was warping beneath us. Our measurements were always relative, always a guess. Now picture a new instrument suspended from the ceiling high above the center. This device is not touching the tub, not influenced by its movements. It sends down a continuous, impossibly thin probe of energy. This probe touches the water's surface and instantly reflects back. The tool measures the round-trip time with a precision so staggering it can detect a change in the water's height smaller than a fingernail. It does this not just in one spot but across the entire surface, weaving a complete tapestry of the water's topography in mere days. This is what satellite altimetry has given us. The cosmic vantage point, the stable reference frame, the unwavering gaze. We have moved from dipping sticks in the mud to scanning the entire planet. This extraordinary capability was not born overnight. It was the culmination of decades of daring, a testament to scientific persistence. The story begins with a machine that became a legend. In the summer of 1992, a new eye opened upon the world. Launched into the void, the satellite Topex, Poseidon was a marvel, a joint mission between NASA and its French counterpart CNES. It was an audacious gamble, a proof of concept on a planetary scale. Many in the scientific community were skeptical. Could a machine orbiting 1300 kilometers above the Earth truly measure the height of the sea with centimeter-level accuracy? It seemed an impossible task, a fool's errand. The challenges were immense, almost beyond reckoning. The satellite's own position in space had to be known with surgical precision. Its orbit had to be a perfect repeating track, a celestial railway line, The microwaves it beamed downwards had to penetrate the atmosphere, a journey fraught with distortion. Water vapor in the air could slow the signal, tricking the instrument into thinking the sea was lower than it actually was. Charged particles in the ionosphere could introduce their own deceptions. Even the ocean's surface conspired to complicate the measurement. It is not a placid mirror, but a chaotic canvas of waves and swells. The radar pulse would not reflect from a single point, but from a wide, churning patch of water. The instrument had to intelligently average these chaotic returns to find the true underlying sea level. It was an endeavor that pushed the boundaries of rocketry, of computation, of our understanding of the Earth's own gravitational field. Against all odds, it worked. It performed miracles. Topex, Poseidon, began to paint a picture of our oceans that no human had ever seen before. It revealed the vast hills and valleys of the sea surface topography, sculpted by gravity and massive circulating currents. It charted the gargantuan oceanic eddies, storms of water hundreds of kilometers across. It gave us our first true glimpse of El Niño developing in the Pacific. Most importantly, it established a baseline, a starting point for a continuous, unbroken record of change. It began the most important watch in human history, the tracking of global mean sea level. When its mission ended, its legacy was immediately taken up by a series of successors. The Jason satellites, Jason 1, Jason 2, and Jason 3 were its children, each one a more refined, more capable version of the last. They were built to ensure that the stream of data would never be interrupted, that the watch would never be broken. This chain of observation has now endured for over 3 decades. It is one of the crown jewels of climate science. A dataset of such length and precision that its conclusions are undeniable. It has chronicled the subtle accelerating rise of the global sea. Millimeter by millimeter, year after year, the line on the graph has crept upwards, and now the responsibility for maintaining this sacred vigil falls to a new generation of sentinels. In a sterile, brightly lit chamber shielded from the dust and chaos of the outside world, a new guardian was assembled. Here, in this clean room, the air is filtered to near perfection. Technicians clad head to toe in white protective suits move with quiet deliberation. They are the stewards of a multi-million-dollar creation, a concentration of human ingenuity destined for the vacuum of space. This is where Sentinel-6B was born. It is a dense, intricate assembly of electronics, antennas, and solar panels. At its heart lies the Poseidon 4 radar altimeter. The latest evolution of the instrument that flew on Topex, it is a masterpiece of remote sensing technology. It operates on a principle that is elegantly simple in concept, yet breathtakingly complex in execution. The device fires a short, powerful pulse of microwave energy downwards. This pulse travels at the speed of light, an invisible spear cast towards the planet. As it descends through the atmosphere, a suite of secondary instruments is already at work, characterizing the medium through which it passes. A radiometer measures the amount of water vapor, providing the crucial data needed to correct for atmospheric delay. Other systems map the ionosphere's electron density. Every possible source of error is anticipated, measured, and accounted for. The pulse strikes the ocean surface and scatters a portion of its energy, reflecting directly back towards the satellite. The satellite's sensitive receiver captures this faint echo. The entire journey, a round trip of over 2,600 kilometers, takes less than 9,000ths of a second. The onboard atomic clock, a timekeeper of unimaginable stability, records this interval with picosecond resolution. This time measurement is the fundamental datum, the raw truth from which all else is derived. From this sliver of time, engineers and scientists can calculate the distance between the spacecraft and the ocean surface with astonishing fidelity. This process repeats thousands of times per second as Sentinel-6B hurtles onward. It moves at 7.5 kilometers every second, circling the entire globe once every 2 hours. Its orbit is meticulously designed to cover 95% of the world's ice-free oceans every 10 days, a relentless systematic survey weaving a new map of the planet's seas. It is not alone in this task. It flies in formation, with its identical twin Sentinel-6A, which was launched in 2020. That satellite was renamed the Michael Freilich in honor of a visionary NASA director. Together, these two spacecraft ensure there are no gaps in the record. One follows the other in the exact same orbital path, creating a seamless handover, guaranteeing the continuity of this vital climate record. The construction of such a machine is an act of profound optimism and deep concern. It is an international collaboration, a pooling of resources between Europe's EUMETSAT and ESA, and America's NASA and NOAA. A global problem demands a global response, and this satellite is its physical manifestation. Its purpose is solemn, to bear witness to a world in transformation. The moment of its ascension approached on a cool California morning. Vandenberg Space Force Base, a rugged stretch of coastline north of Los Angeles. Here, the land meets the Pacific in a dramatic clash of cliffs and surf. A persistent marine layer often cloaks the launch pads in a thick grey fog. It is from this dramatic stage that Sentinel-6B would begin its journey. Atop the launch pad stood the vehicle of its deliverance, a SpaceX Falcon 9 rocket. A slender, two-stage booster, tested and proven a workhorse of the modern space age. Inside the rocket's payload fairing, the satellite waited in darkness. Its final checks complete, its internal systems dormant, awaiting the call to orbit. For the launch teams, these final hours are a symphony of controlled tension. Thousands of systems are monitored, thousands of procedures executed. Propellant loading begins, the rocket venting plumes of super-chilled oxygen vapor, hissing as it is filled with the volatile fuel for its momentous climb. The countdown is the final cadence, a ritual that focuses the mind. 10, 9, 8. The world seems to hold its breath. 7, 6, 5. At the base of the rocket, the pre-valves open. 4, 3, 2. A torrent of water floods the launch mount to suppress the violent acoustic energy. 1. Ignition. Liftoff. A flash of incandescent light banishes the morning gloom. 9 Merlin engines roar to life, a controlled detonation of immense power. For a heart-stopping moment, the rocket is held down by clamps, its onboard computers verifying that all engines are burning with perfect thrust. Then the clamps release. A machine weighing over 500,000 kilograms begins to rise. It ascends with impossible grace, a pillar of fire against the coastal sky. The sound arrives a few seconds later, not as a noise but as a physical force. A deep crackling roar that vibrates through the ground, through your bones, a visceral announcement of the energies being unleashed. The Falcon 9 climbs, gathering speed, pushing against the crushing force of gravity. It becomes a brilliant star arcing out over the Pacific. Within minutes, it is traveling faster than a rifle bullet. The mission milestones tick by with flawless precision. Main engine cut off, the first stage separating to begin its own controlled descent back to Earth. The second stage engine ignites a single vacuum-optimized powerhouse that will push Sentinel-6B the rest of the way to orbit. The protective fairing, its job done now that the satellite is clear of the dense atmosphere, splits open and falls away. For the first time, the satellite is exposed to the raw environment of space. The second stage burns for several minutes, a long, silent push into the void. Then it too falls silent. The vehicle is now in a parking orbit, coasting. It is a moment of deceptive calm in a highly dynamic sequence. The spacecraft drifts over the frozen wastes of Antarctica, gliding towards the precise point in space where it must be released. The final command is sent. Small pneumatic pushers gently nudge Sentinel-6B away from the spent rocket stage. It is free. Slowly, gracefully, it drifts into its own independent existence. There is no sound, only the silent, inexorable laws of orbital mechanics. Onboard computers awaken. The satellite begins its automated deployment sequence. 2 vast solar arrays folded like origami for the violent launch, unfurl like the wings of a metallic insect turning to face the sun. Their blue photovoltaic cells begin to drink in the light, powering the electronic mind and senses of the nascent Sentinel. Down on Earth, in control rooms in Germany and the United States, a signal is received. A simple stream of telemetry, a whisper across the void. It confirms that Sentinel-6B is alive, healthy, and ready for its mission. A quiet wave of relief and triumph washes over the teams who built it. Their creation has survived its fiery birth. Now its long watch can finally begin. What has this unbroken 3-decade-long vigil from space revealed? The message, written in the cold, hard language of data, is stark and unambiguous. Since 1993, the global average sea level has risen by more than 10 centimeters. That may sound like a trivial amount, the width of a human hand, but to dismiss it is to fail to grasp the scale of our planet. To raise the entire world's ocean by even 1 millimeter requires an almost unimaginable volume of water. Over 360 billion tons of it. This rise is not a steady linear process. The data shows a clear and terrifying acceleration. In the 1,990 seconds, the rate of rise was about 2 millimeters per year. In the last decade, that rate has more than doubled, now exceeding 4.5 millimeters per year. The curve is not just going up, it is steepening. The planetary fever is getting worse. Sentinel-6B and its predecessors have allowed us to dissect the causes of this swelling with unprecedented accuracy. The diagnosis points to two primary culprits, two planetary symptoms. The first is a simple consequence of physics' thermal expansion. Our planet is warming. Over 90% of the extra heat trapped by greenhouse gases has been absorbed by the oceans. The sea has acted as a colossal buffer, protecting the atmosphere from the full extent of the warming we have caused. But this service comes at a price. When water heats up, it expands. Think of the global ocean as a single massive body of liquid in a planetary container. As we add heat, the individual water molecules gain energy. They begin to move faster, jostling against each other more vigorously, pushing each other slightly further apart. This microscopic expansion, multiplied across the incomprehensible volume of the Earth's oceans, translates into a significant rise in the surface level. For the first half of the satellite record, this phenomenon was the dominant driver. The ocean was swelling from within like a body with a fever. But in recent years, a second, more ominous driver has begun to take the lead: the melting of land-based ice. The great ice sheets of Greenland and Antarctica and the world's mountain glaciers are vast frozen reservoirs of fresh water. For millennia, they existed in a delicate balance. The accumulation of new snow in their interiors was roughly equal to the loss of ice at their edges through melting and iceberg carving. That equilibrium has been shattered. Satellites like Sentinel-6B can see this happening. While their primary mission is to measure the ocean, their precise orbits also allow them to map the changing height of the ice sheets. They have watched as the surfaces of Greenland and West Antarctica have slumped and lowered. The data is unequivocal. They are losing mass at a staggering rate. Hundreds of billions of tons of ice are vanishing every single year. This is not sea ice, which is already floating, and does not affect sea level when it melts. This is ancient ice piled kilometers thick on solid ground. When this ice melts or flows into the sea, it is a net addition of water to the oceans. It is like turning on a faucet in our planetary bathtub. And that faucet is being opened wider and wider with each passing year. This is the source of the acceleration seen in the sea level curve. The contribution from melting ice is now the largest part of the problem, and it is growing faster than the models once predicted. The sentinels in space are not just measuring the symptom, the rising water, they are also monitoring the disease, the decay of the world's cryosphere. The consequences of this inexorable climb are not some distant, abstract future. They are happening now. They are being felt by millions. A few millimeters of rise per year compounded over decades translates into dramatically more frequent and severe coastal flooding. A storm surge that was once a 1-in-100-year event now happens once a decade in many coastal communities. High tides now regularly flood streets in cities like Miami and Venice, even on perfectly sunny days. This is the tyranny of shifting baselines. The entire system is elevated, so every storm, every high tide starts from a higher launch pad, pushing floodwaters further inland than ever before. The intrusion of salt water contaminates coastal aquifers, poisoning the freshwater sources upon which millions depend for drinking and agriculture. It destroys coastal ecosystems, salt marshes, and mangrove forests, which themselves are critical natural defenses against storm surges. Entire nations, low-lying island states in the Pacific and Indian Oceans face the real and imminent threat of complete inundation of national extinction. The data from Sentinel-6B is not merely an academic exercise, it is an essential tool for adaptation, a lifeline for coastal planning. It informs where to build seawalls, how high to elevate infrastructure. It helps predict which areas will become uninhabitable and when. It is a stark numerical warning that provides the foundation for the most difficult conversations our civilization must now have. It is a map of our changing world delivered from on high. The future projected by this unbroken data stream is profoundly sobering. Even if we were to halt all greenhouse gas emissions tomorrow, sea level rise would continue for centuries. The ocean has a tremendous thermal inertia. The heat we have already added will continue to cause expansion for a very long time. The ice sheets, too, have crossed critical thresholds. Many glaciers are now in a state of irreversible retreat. We are already locked into a significant amount of future rise. The critical question the one Sentinel-6B will help answer is how much and how fast. The difference between 1 meter of sea level rise this century and 2 is the difference between a manageable crisis and a global catastrophe. It is the difference between saving some coastal cities and abandoning all of them. The mission's data will be crucial for refining our climate models, for narrowing the uncertainties, for giving us a clearer picture of the road ahead. It will watch for the awakening of sleeping giants. Scientists worry about non-linear tipping points. The potential for the sudden rapid collapse of the West Antarctic ice sheet, for example. This single body of ice contains enough water to raise global sea levels by over 3 meters. The satellite's altimeter will be one of our first lines of defense, watching for the telltale signs of acceleration and structural weakening that might presage such a catastrophic event. It is our early warning system for the unthinkable. There is a deep philosophical poignancy to this mission. For centuries, we have looked to the stars for portents for meaning. We have projected our myths and our anxieties onto the heavens. Now, in a remarkable reversal, the heavens are looking back at us. We have placed our own creations, our own dispassionate intelligence into orbit to observe the consequences of our own actions. The satellite is a mirror. It does not judge, it does not editorialize. It simply measures and reflects the truth of our world back to us. It is a testament to what we are capable of at our very best. The international cooperation, the decades of scientific dedication, the exquisite engineering, the relentless pursuit of knowledge. And it is a chronicler of our greatest failure, our inability to live in balance with the planetary systems that sustain us. Sentinel-6B is both a triumph and a tragedy encoded in a single machine. An eye in the sky watching the fever of the Earth manifest as the slow, silent swelling of the deep. Its mission will last for years, adding to the data record, strengthening the signal, resolving the picture of our future. It will be replaced in turn by another, and perhaps another after that. The watch must not be broken, because in the quiet, precise and relentless stream of data beamed down from this celestial watchman lies the irrefutable story of our rising seas. It is a final, urgent message spoken not in words but in millimeters, a warning from our planet relayed from the stars. And the question that hangs in the balance is a simple one. Are we listening?